Okay, I think we can get started. And for the people who just joined us, you can go to the hprc.tamu.edu page /training/intro fortran.html. That's the course page for this Fortran class. And you can download the slides to follow along and some example source code given in this file. And so before we begin, I also want to show you like how, so this class, like there'll be a lot of slides and presentation from my end, but you'll also have a chance to like try out the examples for yourself. So we'll code some very simple Fortran. So if this is probably a course best for people who use MATLAB or Python and just want to get the first glance of Fortran, it's a perfect course. So it'll be very simple, and you can stop me whenever you want to ask me questions. So the first thing or the second thing we're going to do is go to portal.hprc.tamu.edu. So if you're on campus Wi-Fi, you don't need a VPN, but if not, you have to connect to the TAMU VPN and then go to this page. And then you're going to click on Grace on Demand portal. And that's going to ask you to log in like usual and request two-factor authentication if you don't already have it. Over here, you're going to click on clusters and you're going to click on Grace Shell Access. And then let me resize my screen. And hopefully my browser window is accessible, viewable on Zoom. Okay. So enter your password, two-factor authentication, then we log in. Okay, so currently you're in your home directory, and to verify that, you can do pwd. So I'm in /home and /netid, right? And so we can do a few things. So /scratch training Fortran. So the ls command just lists all the files in the scratch training Fortran directory. So over here, we see an examples.tar.gz. So what we want is to copy, you can copy, so cp space scratch training Fortran examples.tar.gz and copy it to your home directory. That's a dot. So now your home directory has the examples.tar.gz file. So we'll come back to that. I'll just proceed with some introduction, and then I'll come back to these example files. Okay. So hi, everyone. My name is Abhishek. So I'm teaching Fortran for the first time. I'm following along with my colleague Jin Tao's Spring 21 Fortran course. A lot of the material will be very similar to how it is structured. It's supposed to be a very basic Fortran class. And so this is the agenda for today. And so we'll go through them one by one. And of course, at any point, please feel free to stop me, ask me questions. I think you can drop questions in the chat. I think you can also raise your hand on Zoom if you want to ask questions. So, okay, so we're at the juncture where we need the source code. Okay, so we're going to try to get the source code now. So we go back into the browser, and remember, so I'm going to repeat the steps I did. So I first went to portal.hprc.tamu.edu, clicked on Grace portal. Then I went to clusters, Grace shell access, and then I logged in there. And that's going to give me a screen like this. And presently we're in the home directory. And then what we do is we did this command. So we copied from scratch training Fortran. We copied examples.tar.gz. Okay, and we copied it to the home directory. So it's just a dot. And I think I'll magnify it so you can see better.
I'm on the base now. So where was the file?
So yeah, so you have like two ways of dealing with this. So either were you able to log in to Grace?
I got into Grace.
Okay, so then you're gonna say cp space, you're gonna say slash scratch
Oh,
slash training
okay.
slash Fortran slash examples.tar.gz. So you can actually press tab and it'll autocomplete and stuff. So
And then okay, I see.
yeah. So once you do that, you will have copied the source archive to the current directory. Okay. Another.
You have a dot at the end.
Yeah, there's a dot at the end, at the very end. Okay. And there's also another way to obtain these files. So we already saw in the course directory, we saw a tar file. So you can just click on this and this will get downloaded to your home directory, your local machine, right? And so this file, so now you can go, so remember we went to portal.hprc.tamu.edu. We can go to Grace On Demand portal and then go to files, home directory. So that's again files, home directory, right? And you can click on upload over here, right? And the upload, you can just select the Fortran examples.tar and then it'll get uploaded to your home directory. So that just two equivalent ways, right? So you can use either way, which one you're most familiar with, you can use it. And now is also a good time to drop questions if you're not able to, because this is the first step, right? Okay. So now let me go back to my login. So now we're going to extract that archive. So you're going to say tar space xzvf. Yeah. So this is the command you want. So you're going to say tar space xzvf space the file we just copied, right? And for those who use the web browser method, you're going to skip this z in the middle. So this z over here you have. So it's instead going to be just xvf. So if it's Fortran examples.tar, it's going to be xvf. Otherwise, it's going to be tar xzvf. And what? Yeah.
That's if you're using the portal phrase.
Yeah.
We don't need the C.
Yeah, we don't need the C.
And then you just press enter.
Yeah. So if I do that, okay, sorry about that. I think something may happen wrong.
Okay.
I don't know if I did something wrong. Okay, let me try the other one. worked this morning, so it's weird. Okay, so I'm going to follow the other method, Fortran examples.tar. Okay. And now I have Fortran examples.tar. And let me go back. Okay, so that worked easier. So if the xzvf method works for you with the other file, please go ahead and use it. For some reason, it's not working for me this morning.
And it worked for me. So what worked for you? You uploaded it? Then
Yeah, so what I did was I uploaded it, and then I said tar xvf. So these are just basic Linux commands. So anytime you're dealing with files on Linux, you usually have to compress and archive a bunch of files. And so you always, so tar is for like combining multiple files into a single tarball. And the GZ usually means it's compressed. So here it's just a tarball, so you're just untarring it. Okay. I know that is a little more complicated than it needed to be, but yeah. Okay, so now we're going to go to examples. So you're going to say CD examples, and hopefully everyone got the source code working and it's extracted. And so now you can, so it's extracted to a directory called examples. Okay. So over here, you'll see many programs. Okay. And the first thing we're going to try to do, so you can try this command vim space hello.f90. Okay. So this is like a very basic Fortran program. And at this point, let me know if you're not able to follow along with this. So I'll just go back to what I did. So
still getting errors with the tar.
Yeah, I'll be with you in once. So it's XVF, not CVF. Yeah, so did you upload the file? Yeah. So it's in home directory. Okay, so go back. So you should just use tab. Okay, thank you. Okay, so we will continue with this. So we extracted the tarball, and then we changed directory CD space examples. The slash is not necessary, but so CD examples. And then you're going to say, you can forget, so ls just means list all the files in the current directory, right? And vim is the text editor. So for example, if you're using, if you're a Windows person, you have like Notepad on Windows. So vim is like a notepad, but for the command line. So it's just a way of opening a text file, but using the command line. So you don't have a GUI interface. So I just say vim hello.f90. Okay. And I think maybe I can also provide an alternative. Okay, but I'll come back to that later, I promise. So this is a basic Fortran program, and I'll go to the structure in a bit. What you have to do is, right now you don't have to do anything. As long as you haven't typed any keys, you can just press :Q. So that shows up at the very bottom, right? It's :Q. Doing this exits the Vim program, right? And returns you to the command line, right? So we just open the file just to see what's in it, right? Also, I could have said cat hello.f90. So that just prints everything to the command line, but it doesn't let you edit the files. So anyway, so the first thing we're going to try to do is we're going to see a compiler. So we have a compiler for Fortran. So and I'll walk you through the process of what a compilation is. But for now, I want you to try Fortran. That's G and Fortran. And then you're going to say hello.f90. Okay. When you run this, what becomes the output is a file called a.out. Okay. That is like the standard name whenever you compile any Fortran or C program, C++, they usually result in an executable called a.out. Now this a.out is not a text file, so you cannot open it with Vim, but it's an executable file. And so what that means is, if you're coming from a Windows background, it's a .exe file, and you wouldn't try to open a .exe file in a notepad, right? You're gonna try to execute the .exe file. So how do we execute that? So you say ./a.out. Okay. So the first step was compilation. You said Fortran hello.f90. And if that is successful, then it produces a file called a.out. And so then you're going to run that compiled Fortran file. So you're going to say ./a.out. Okay. And hit enter. So it's asking for a name. So you can just enter whatever. And so it's basically, it's a program to read in your name and then greet you with a hello. So it's a very simple program. But here we walk through the process of compiling the program and then executing it, right? Any questions till that point? Like everyone able to keep up with this? Okay. Okay, so coming back to our slides. So this is, so basically a hello world, if you're not familiar, it's like the basic, it's the first thing people write to like learn a new programming language or a scripting language. So it's like just a main program and, it's printing hello statement. But in our code, we read in the name and also like printed out the name. So it's, and remember we said Fortran hello.f90, but here the syntax is a little more complicated. So when you say, let's go with hello world.f90. So if you said Fortran hello world.f90 and you skipped this -o hello world in the middle, then the executable you're going to have is going to be ./a.out. But that's not very, it's like, let's say you compile 5 different codes. If everyone is named like a.out, that's like very confusing. So you want to name the executable to a more understandable name, which is why you have this -o. So so in this case, we're compiling hello world.f90 and we're naming it hello world. So the executable is named hello world. So in the next step, you do ./hello world instead of ./a.out. So just a little bit of nuance, right? Okay, so some basics. So what is Fortran? It's basically, it's in the name. It's like formula translation. So long back, like I think about like 1956, IBM developed this primarily for doing like scientific and engineering computations. So, and if you're from like, I mean, pretty much if you're using programming, you have some sort of a logic in your mind, and you want to try to translate that into a more formal construct. And Fortran, is like like one of the simplest languages in that aspect. It's like you can keep it as simple, like no complex programming constructs or anything like that. It's as simple as you want to be. That's how it started out. So it's like a very basic program to, like, for example, if you want to compute the area of a circle, you can, whatever you do on pen and paper, you can literally translate that into code. So it had like very simple origins. They didn't even have like computers like what we have right now. It was like punch cards, things were like very, very simple. And then slowly Fortran added a lot of features over time, and it's now a much more full-fledged language. And so back then, a lot of what it was used for, and a lot of what it's still used for, is like numerical weather prediction. So my background is I work in a climate modeling lab, and most of our codes, the real workhorses, they're all in Fortran. And these are like million lines, a million and 1.5 million lines of like Fortran code alone to do like some real heavy lifting, like weather and like climate modeling stuff. So it's proven itself time and again. It's a very capable language. It's constantly used for many purposes. And of course, like a big question on your minds would be, why still learn Fortran? It's like, isn't it antiquated? And so there are a few reasons for that. Few reasons to like stick with Fortran. It is still a great language for scientific computing, especially the ones that need to scale a lot. And what do I mean scale a lot? Like it's one thing to write a program to like compute the area of a circle, or like, let's say that's like a very simple program, and it doesn't matter which language you use it. It could be a very slow thing, but it's going to run very fast. But now, instead of like, now think of like, for example, like modeling the climate of like this whole planet over 500 years or like 1,000 years. That's like complicated in more ways than you can imagine. And that's like an extremely enormous like workload, even for like the world's fastest supercomputers. And so the thing is, if you use a programming language like MATLAB or even like Python for that, it's not going to be as efficient towards that. And Fortran, like it's got like over the years, like there's been like so much development in like compiler technology that Fortran has like remained on par with C and C++ in terms of like execution speed. So my background was like, I was a computer science major, and then I shifted to like engineering, and I saw Fortran. In my computer science background, I never learned Fortran because it was considered old. And then I switched to engineering, and now people are using Fortran. And I was like, why are they still using this really old language? And then I slowly was introduced to like the performance like metrics. And it's like with compiler optimization, Fortran can like beat C++. It's like basically no difference. And what Fortran gives you better than C or C++ is like array handling, especially for scientific computing. People use a lot of arrays, and you want to reshape it or like multiply it in like very simple ways. Maybe if you're familiar with MATLAB, MATLAB can already do that, but it doesn't scale this much. Fortran is much more easier to learn than C or C++. And of course, it's got tons of mathematical libraries that you can simply make use of instead of rewriting it yourself. Okay, and most of the Fortran codes these days are parallelized, so they run on like really big supercomputers. So some history. So first developed by IBM in 1956, and you see that it's continued on with development, and it's become like more standard, and like what we are going to be dealing with is Fortran 90 and the 95 standard typically. So there are a lot of differences, and like if you're interested, you can look at the differences between Fortran 90 and 77. Even though some aspects of the programming structures will look similar, there are also like quite a bit of differences, which we'll probably not have time to cover in this class, but you can search for it and you can ask me later. And then since 95, there have also been like more developments. If you're familiar with object-oriented programming, Fortran can do that. And it can also do some of the more like, it's really kept up with the times in that sense. Okay, so some very basics here. If you use the computer, you know what a hardware is and a software is. Hardware, of course, the physical medium. And in our case, the hardware is also Grace, the supercomputer, which is sitting in a data center. And whereas the software is the Fortran thing and even the operating system. So there's an entire stack of software that we often don't think about, but there's so much going on underneath, right? And we used VI or Vim, which is a text editor. That's a software, right? So basically, what a compiler is a piece of software, but what it does is it translates the computer program we wrote, which is understandable by us, right? Because it obviously needs to be understandable by us because we are writing it. But then the machine cannot execute something like that. The hardware is still expecting data to be, like instructions and data to be in binary. So zeros and ones, right? So somebody has to do the business of translating this higher level text, like Fortran program, to like binary, right? And so either binary or like assembly language, and so the compiler makes that happen. And so some of the most popular Fortran compilers are listed. So we're using the GNU Fortran, which is like the open source Fortran associated with the GNU project. And there's also Intel, which is paid. We have it on Grace, but it's but outside of Grace, you still, you have to pay for it. And there's also Cray, Portland Group, PGI, and all that. Okay, so a typical Fortran program. So this is the high level thing that is accessible to us. Like I said, the compiler compiles this and generates the object code that is understandable by the machine, right? So to tell, so who is executing the object code? It's the operating system. So in our case, on Grace, it's a Linux operating system. It's a CentOS operating system. But you could equally compile this on Windows or a Mac, And in all of these cases, in your Fortran program, you have to tell it where to begin. Like, let's say you have a series of lines in a Fortran program. The compiler, the operating system doesn't really know where to start. And to tell it where to start, we have the program statement. So that is basically the starting point, or like the main, if you're coming from C or C++, that's like the main program. So to define it, we have program name. And then we have this thing called implicit none, which I'll come back to later. And then we have the so-called specification part, the execution part, and the subprogram part. So, and finally, so all you need to be aware at this stage is there's a program with a program name, and then you need to, after it's over, you have to end program name. So you start a program, end the program, right? And then whatever is happening inside is just instructions, which should happen in the program. Okay, so now let's start, look at a very basic example, right? So in this example, we're doing the square of a number. So the first line is program, which is a keyword, which I should have also mentioned here. So the ones in blue, the things you're seeing in blue text, they're keywords. And what they mean is when you type in the, when the Fortran compiler sees that Fortran keyword, it has a special meaning to it. It knows what to do with the following text, right? So program square tells the compiler that it's a new program and its name is square. And but you can also tell the compiler that you have some lines in the text that are purely for like either annotation or like decorative purposes. So that's called a comment, right? Just to keep track of like what this program is doing. So for a comment, you're going to have an exclamation. So a comment starts with an exclamation in Fortran. In other languages, you have different characters to start the exclamation, sorry, to start the comment. So anything following that exclamation is a comment. And this thing, implicit none, I will come back to this later. And then in the next line, what we're doing is we're declaring what is a variable. And so what is what's a variable? A variable is just, so when I declare x or x underscore sq, it is intended that they will have values in the program. For example, x could have a value of 1.3 and at one point in the program. And then later it could be like, we can change the value to 2.5. So that's the, literally the function of it is in the name, that it's a variable. And so saying it's real means we're just giving it a type. And I'll come to that in a bit. And so basically what we're doing here is this program tries to ask the user for a value of x, and then it tries to print what the square of x is. So, so you see some variable definition and then just some statements, right? Either printing to the screen, reading from the screen, and then actually doing the squaring. So all these are just statements, right? But we'll pay more attention to it later. And then we end the program with a square, right? Let me quickly check if I have questions. If you have questions, drop it in the chat. And okay, so the Fortran source code, in Fortran 90, 95 and later, we have what is called free format source code. And I think so I think what you need to be aware of for this thing is that in the previous versions of Fortran, you had a lot of restrictions on like how you could write the code. So for example, if you look at this, you see the write statement is like this long. That would be different in Fortran 77. And because this is not a class about Fortran 77, I don't want to go into it, but we can, go into it later if you have questions. The Fortran program is case insensitive, which is a big difference from many other programming languages. So what does that mean? Here I said everything is in capitals, right? But the program could be everything in small letters, or it could be in mixed case, like this program over here, and it wouldn't matter. Fortran thinks it's the same thing anyway, which also means that if you have a variable defined as small x, you cannot have another variable defined as capital X, because they'd be the same thing. So you cannot define them twice, okay? But it is strongly advisable not to change the case throughout the program. Keep them, like whatever notation you're using, keep them consistent for readability purposes. Otherwise, it's you get lost. Like you come back to your own code after a week, you will not understand. So that is why you also add comments, right? Because it's like, it's clockwork. You think, oh, I wrote this code, I'm gonna, know it. And then you just give it a week or two and you come back to it, and like the more complex the code is, the more you're like lost in it. So statements. So all these things we saw here, pretty much everything within the program and the end program, except for the comment, right? All these are just statements. They're just different types of statements. So they're like executable statements and non-executable statements. Executable statements are those which are executed at runtime. So what is runtime? Remember when we did ./a.out, that's when we are running the program, right? So that is runtime. But when we did gfortran hello.f90, that's compile time, because that's when it was compiling. So there's compiling and there's running, right? So executable statements actually run when you execute the program, right? And non-executable statement provide other information to compilers. So we're probably not going to cover that much in this class. If a statement is too long, it may be continued by ending the line with an ampersand. So I think we'll come to examples for that. The maximum number of characters in a line is 132, but for like just readability purposes, it's good to limit it to 80 characters, 80 character width. That is, if write the statement cannot go past 80. So yeah, it cannot go past 132, but we recommend that you keep it to 80. Multiple statements can be written on the same line, provided that the statements are separated with a semicolon. So you can have read x and y equal to x squared on the same line, but you need to have separated them with a semicolon, right? Okay, I already sort of explained what we think of as a variable. It's like one of the, basically if you're writing a program that has to do anything important, you need a variable. So the way you define variables, there are some rules to them. So it may consist of 31 alphanumeric. So basically A to Z, both caps, lowercase, and numbers. It can also have underscores, but the first character must be a letter. It cannot be a number. It cannot be an underscore. It must be a letter. Okay. And there are no special symbols allowed. No @ it's not like entering a password. It's like you have to adhere to these rules. And variable name should not contain a space. Okay. So so we talked about variables. We also saw in this example that we defined a variable type real. So what is a variable type? So Fortran by default allows for a few different classes of data. If you have like whole numbers, like integers, you can just stick with the integer data type. But if you're doing some scientific sort of computations that rely on like, there's a typo here, but fractional numbers, so real numbers, then you can define the real type, use the real type. Less commonly used, but if you're also into like a math involving like complex variables, there is a type for that, which C or C++ doesn't have, and many other programming languages don't have. Logical, they just have a true or false value. So they don't store numbers, they just store whether it's true or false. And there's also character data type, which can either store a single character like A, B, C, whatever, even letters, but letters need to be in a character form. Or they can contain whole strings like hello world, right? And so these are the intrinsic data types. So what intrinsic means is the data types that come with Fortran, like standard. So you don't have to do anything else to use these. But users are able to define their own sort of data structures, which is more advanced or intermediate Fortran, I have to say. Yeah, you can ask me more questions about that later. So real is the single precision floating point numbers. So at this point, you may have a question about why do we have integer and real? Like, why can't we just have real and skip integers? Aren't integers like a subset of real? Well, the reasons for them are like manifold, like, okay. But some of the basic reasons, so when you integers are represented exactly on a computer. So for example, if you have an integer which is 5 or 10, a computer can exactly represent it. So there is no question, it's not approximately 10 or approximately 5. But what about like a value like pi, which, like the decimal places keep on going, right? Like as far as you want to. So how does a computer store that? And the answer is it has to truncate them. So with a real type, a real provides a single precision type. I have a question. Okay, I'm going to answer a few questions here that I see. Okay. In terms of the first question, what does the star stand for in the read on the write statements? We're going to come to that. Okay, thanks for that. Is the y equivalent to SQ in the squared program? Okay, actually, that's a good catch. So the y needs to have been defined up on top here. So if you try to execute this code, it would throw an error. So that's a good question. So before using any variable, you have to declare them, right? So before reading in X, the compiler has to know what X is. It cannot be anything. It has to know what type it is, especially because you said implicit none. And there's a reason for that, which I'll come to soon. So Y also must be over here, okay? Can we include special characters? in the variable, if you're talking about the variable names, you cannot have other special characters. Okay, so the star over here, we'll come to that later. These two stars here, that means it's squared. So y is x squared, okay? So coming back to what I was talking about in terms of single and double precision. So come back to the example of pi, right? So all I know is like 3.14159, and some of my friends can recite like up to 100 decimal places. But basically it goes on to like infinity, right? Like, so that's sort of a research problem in itself. But in a Fortran, if you use the real data type, by default, it can maybe remember up to 7 decimal places, 7 or 8. It depends on how much data. And why is that so? Because when you say real, the system understands, the compiler understands that you're only going to give it a certain amount of memory in the computer to represent that variable. So when you said x was a real and y was a real, it can only represent so many decimal places. So you can never exactly represent the value of pi with a real. To make things a little more accurate, you also have a double precision, which basically doubles the amount of the data you can store, right? And so you can make pi a little more accurate. But again, as you see, it's like you're limited, right, by the amount of memory you have. So some examples. So integer, like 242, the integer can be positive or negative. And the integers, so there are limits to how big the integers can be. Just like for the real numbers, you have limits on how many decimal places it will go to. For integers, there is a cap on what the maximum number is. And for that, you should refer to the Fortran documentation, because it's also very platform specific. So if you, for example, if G-Fortran running on Linux, or even a certain kind of Linux, will have a certain max, certain cap, whereas the Intel version will have a different limit. So this is a real number, some examples of real numbers. And again, real numbers can have positive and negative values. And this one is a double precision equivalent of the same thing. Over here, we use the D notation here just to represent that it's in fact you're asking the compiler to store it in a double precision manner. And just some examples of complex numbers are actually very simple. It's just 2 real numbers combined together. It's like a complex number you might know is like you'll have a real part and an imaginary part, a plus ib. Here a and b are both like real numbers. So a complex is just 2 real numbers combined together. But you can also have double precision complex numbers. And logical values, as I mentioned, they can be either true or false, but note how we have a dot in the front and at the end. So dot true, dot false, dot. Okay. A character can just be like hello world and is like whatever string you want. So within double quotes, right? And so I guess I can show you some examples at this point, maybe. And one thing about this terminal, I think if you're absent from it for a while, it sort of disconnects. So in which case you just go back to clusters, go to Glacial Access. Okay. So let's go to a simple hello world. Okay. So this is like a simple program I have. So if I were to define an integer, hopefully people on Zoom can see my screen. Okay. And can folks here see my screen? Is it?
No, there is no.
Okay. I don't know if it's possible to. So, okay, I'm going to do something else then. I'm going to come on. Let me quickly try this. Yeah, that's a good idea. Thanks, Magnus. So another thing you can do, which I guess I didn't mention because I don't use it very much, just go to this file, and we already talked about how to go to this file viewer, right? So you just go to the portal, and you can go to home directory. That's going to open up something like this. So I went to my examples directory, clicked on hello, and I clicked edit. And then I go to file editor, and you get this. Okay, this is actually very nifty. And I should have started with this and not Vim. So if you want to use this to edit your programs, that'll be even better. Except I'm going to open hello world. Okay. It's probably good, I think. Okay, so we have a program hello. Okay. So first I'm going to define so actually I'm going to do a couple of things. So over here, I'm going to say I equal to 0. Okay. And then I'm going to modify this thing a little bit because we don't need the code. So you just need to follow up, follow this, and I'll show you where I'm at. Okay. Hit save. Select the downside. Zoom. Okay, now I'm going to try to compile that program. Hello world.f90. Yeah. And this is just for an illustration purpose, so you don't actually have to try it. But if you want to, go ahead.
For this one, when we compile it, you want to give us another executable? Because we already have one.
Yeah, it's fine if it's overwritten.
Okay.
Yeah, but remember how you mentioned you can also use -o to change the name. So okay, I'll also mention that.
Will this also work if you just want to compile like a program that's not like full program, like some sub little module, for example? I know
That's a good question. Yes and no, because you have to change it slightly. You still have to use Fortran or iFort, whatever you want. But it's slightly complicated, and I can, explain that in a little bit after, like during a break or something. Thanks for the question. Okay, so just to recap, I just said I, and then I'm just printing the value of I. And to answer the question, you can just say Fortran hello I can give it my own name. I can call it test. I just say -o test. Okay. And it created a new thing called test. And you see how it's in green? That means it's an executable. I mean, of course, it's not always green, but usually executables have some sort of a color scheme. So here, I'm now executing test, okay? So the value of I is 0. So the code seems to be working. It seems to be doing something. I just said I equal to 0 and printed out the value of I, right? So I have a question. I never said something like this. So basically, I never told the compiler what the data type of I is. So why did it work? Yeah.
Because the implicit is not there, and they think I is some real or energy. I don't know what
Yeah.
the implicit type is.
Yeah, so that's exactly correct. So in the previous case, we defined a variable with, so we didn't define anything. I just said I equal to 0, which is not a variable declaration. It's a variable assignment. Usually we declare or define a variable type before we assign it with a value. But Fortran has some weird things, and it's very important to be aware of that. So what Fortran does is it just looks at the first character of your variable name. If it starts anything from I to N, it automatically assumes it's an integer. So, which you think may be very convenient. It's like, or if you want to use an integer, just start the variable name with an I, or an N, and everything else will be like real, right? But it's very dangerous because it's now like standard Fortran practice. So what the name for this thing that Fortran is doing is called implicit typing. So implicitly, it's just assigning a type to our variable without us knowing, because it's expecting it'll follow these conventions. So it's like, if it's I through N, assign it as an integer, otherwise they're real, right? So in our case, even though I didn't have this, it assigned a thing. To prevent this, and you have very good reasons to prevent this, because there are like so many reasons why it's not recommended to let Fortran do this automatically, the implicit typing. To prevent this and to enforce explicit typing, we say what is called implicit none, okay? So we're going to try the same thing, but with implicit none, okay? And I'm going to compile this program now. So now it's complaining. So it's saying the symbol I on this line has no implicit type. And it's complaining because we added the statement implicit none. So it's an instruction to Fortran to not do this, right? So how do we get it to work? We just define it like we need to, right? So we just say integer : I equal to 0. So now it works. And if you type it, this will work, okay? So that is the meaning of the implicit none statement. With the implicit none, you're going to have to define the variable. And it's always good practice to define or declare the variable. Okay, so I think I made that point. Okay, and I think I gave an example of how to declare variables. And so it's just, you have to start with the data type. Start with the data type, integer, you can have a space between the data type and the double, the two double colons or the two colons. And then all the spaces are for readability, but the space is not strictly necessary. Here, what we're doing is we're declaring I and J on the first line, but for J, we're also automatically assigning it a value of 2 to begin with. So these are just some ways for you to like. So in our previous example, I said integer I equal to 0, but I could have said integer I and then I equal to 0. Okay, it's pretty much the same thing. Okay, and actually this is more or less recommended to do this and not to initialize the value at the start of the line itself. So this is more recommended practice. Okay, so similarly for real, we say A comma B, but for B, the interesting thing is we use the D notation. So it means it's like double precision. So even, so A is only going to be single precision, but B is actually being stored in double precision. And complex numbers are like this. Okay, so now we talked about variable declarations. What if you don't want variable? What if you just want a constant? So this one shouldn't say variables here. It's just constants. So what if you want a constant? So for example, in your calculation, let's say area of the circle, you're going to compute the value of the area of the circle. So you need the value of pi, right? So pi doesn't need to change. So, so how to write code in which you enforce that the value of pi is not going to change. If you try to change it later, it's going to throw an error. So for doing something like that, we use the parameter keyword. So what do we do? So I'm going to copy this. So I can just say, let's say real. So you can say real slash comma parameter, and then we say pi. Okay. Yeah. And doing so means later in the program, you cannot change the value of pi. So for example, if I try to change the value of pi to 5, okay, just for fun. So it'll throw an error, which is what you want. Okay, so that's what a parameter does. Of course, you can have logical variables. Similarly, they can have true or false values. And with character variables, it's so you can set, you can specify the length of the character variable. So you start at the character, just like any other data type, but then you say len equal to 10. What that means is, just like we had real and double precision data types, Fortran doesn't want to allocate like infinite number of spaces for you to like just define whatever strings you want, right? So it's trying to be conservative about how much memory it's trying to allocate. So here saying len equal to 10 means you can only store a string of like 10 characters maximum. And the characters also include like spaces in the between. So basically anything between the single quotes or the double quotes. So if you don't use this len, like in the second line, so you have character, colon, ans equal to yes, it assumes a len of 1 by default. So now it's only storing the first character, even though you said yes, it's only storing y as ans. Okay. So the kind parameter, I think maybe I'll come back to it later. So The kind parameter basically, we talked about single precision, double precision, and like the pitfalls of like how because it's very machine dependent. Like how much a lot of the things vary between the compilers you use and the operating systems you use, the machines you use, and so on. And the kind parameter is a way to like standardize that thing partially. So I think I'll come back to it later if you have time, and like if you have questions about this, ask me about it. Okay, so now we have coming back to this previous example, gave you a very simple example in which I said y equal to x star star 2. So there are many things happening here. So we know that x is a variable, y is a variable that needs to be defined here. 2 is just a constant, like a literal, it's just a number. But what is this equal to and this double star? So they are what are called operators. So operators basically operate on data. And operators can be so-called unary operators or binary. Binary just means if you try to do a plus b, you see how there's a and b on the either side of the plus. So it's operating on 2 operands. So for example, if you take this power operator, it has 2 operands. So it has x and it has 2. So this is a binary operator. And so is equal to. So equal to is an assignment operator. So this is on the left-hand side, this is on the right-hand side. So it's got 2 operands, right? So that's why it's a binary operator. But you also have things like operators that just take a single operand. So let's look at that now. Yeah. So in the arithmetic operators, you have like addition, subtraction, multiplication, division, and then this is raise something to the power of, right? And then you have relational operators. So what is relational operators? So let's say you have x and you have y, and you want to compare if the 2 of them are equal. So you're going to use double equal to, because if you use a single equal to, you're going to assign the value of y to x. Or let me show you an example. Okay, so in this case, I have pi equal to 5. So what this means is it's an assignment operation. Or this is technically incorrect, so let's skip this. So I equal to 0. That's an assignment operation. But I could also say I equal to 0. What does that mean? This means it's a conditional operation. So this is checking if I has the value of 0. If so, the output of the statement will be true. If not, it'll be false. But it's not actually assigning 0 to I. This is the assignment, and so this is the condition. And of course, you can also say things like, is I greater than equal to 0, I greater than 0, less than, So that's these operations, the relational or conditional operation. The last one, slash equal to, means it's not equal to. You're just checking, it's like the opposite of this condition. And so logical operators, so we already, logical operators basically operate on logical operands. So in this case, you can be like, I think actually example is coming up, maybe, no. Okay, so let's say you have 2 logical variables, A and B. So I'm giving A a value of false and B a value of true, okay? And I'm also going to have a C. So I'm going to say C equal to A and B, something like this. Okay. So what this is going to do is it's going to do a binary logic operation. So false and true, false, right? So now C is going to be assigned a value of false. So that's what is happening. Okay. So those that's these operations. Then finally, if you have multiple strings and you want to concatenate them, use the concatenation operator. So for if you have a complex expression involving many combinations of these operators, then there are specific rules to interpret how that expression will look like. So for example, I have so an expression like this. So what is the order of what's going to happen first?
Well, it's the parentheses, but exponent.
Yeah, so there are specific rules to interpret what happens. So for example, you can read this expression either from left to right or right to left, and the meaning would be, it may or may not be different depending on what case you're looking at. So for example, we know that 2 is being raised to the power, so 2 is being raised to the power what? Is it 2, or is it 2 over 3, or is it 2 over 3 over 5? So to sort of interpret these things, we have things called operator precedence. And so arithmetic operators have the highest precedence. And of course, all operator evaluations of variables are carried out from left to right. So they go in this direction, okay? And arithmetic operators have the highest precedence, whereas logical operators have the lowest. And so, and even among arithmetic operations, there are certain operators. So basically it goes from this direction, left to right. And so, so basically, that being the case, even among the operators, there are certain operators which are more higher priority. For example, this power is, it takes precedence over the division. So it's actually 1 over 2 raised to 2. It's not 2 raised to 2 over 3. It's 2 raised to 2. And then the division over 3 happens, and so on. But of course, to not have things so complicated, you can just put a parenthesis. And so that's human readable, right? So you can just, now we clearly understand, oh, it's 1 over 2 raised to 2. It's not 1 over raised to 2 over 3. So you add parentheses to simplify how it looks. But even if you didn't add the parentheses, the compiler has its own rules for how it interprets things. Okay. And I could go on half an hour just examples with this, but I'm gonna limit it to that. And so we already talked about what an expression is like. So y is equal to x raised to 2. That's an arithmetic expression. You can also have y equal to sine x. So I could say something like, so I'm going to say y equal to so this is an expression, but where did sine come from? It's sort of a calculator functionality. Where did that come from? So that's what is called intrinsic functions. So Fortran by default provides several categories of functions. The first category, you can think of them as numerical functions, like simple things like absolute value, ceiling, floor, mod, min. So that between, comparing the min of two numbers, the square root, exponent, logarithm, and all that, and like trigonometric functions here. And you also have like functions to operate on strings. So basically string functions. And slightly more advanced, you have array functions. So these are for your reference. You may not need everything. Like you don't need to like understand each one of them to like get started with Fortran. So use them as required. Okay. Okay. So your first exercise is as follows. So write a short Fortran program to convert 10 degrees Celsius to Fahrenheit and 40 Fahrenheit to Celsius. And these are the expressions. So it's like the Fahrenheit temperature is like 9/5 Celsius temperature plus 32, whatever, right? So how to get started? You can either use your command line to create a new program, or I think you can also say new file, and you can say, what is it? Temp conversion.f90. So the files need to have the extension f90, okay? So once you do that, then click on edit, and then you'll be given with this, right? And you're going to start typing this. You can save, and then once you've saved, I'm sorry for the things here. You do gfortran o temp temp conversion.f90, right? So no. So obviously you need to like have a full-fledged program. So that is one of the differences between a compile language and a scripting language like MATLAB or Python. You need to have a proper working, like a full program which does something for the compiler to like execute successfully. If not, it's going to throw an error. And so just some basics. Remember that like we talked about integers and how to define them. So you need to define a new program block, use implicit none. You don't, you can just, you can, define starting and ending like the Fahrenheit temperature, Celsius temperature, and you can write an expression to convert between them. So like just very basic arithmetic, nothing, no intrinsic functions or anything like that. But it's your choice whether to use integers or real for this program. And I'll also come to that, show you some examples in a bit. So yeah, let me know if you have questions about this exercise. Those in person, I can come and help you.
What's the temperature in Celsius? Oh, what's the temperature?
So
Okay.
yeah, I mean, even if you do one of the conversions, that's fine. Okay.
Can you go back to the editor?
Yes. The new one or the old one?
The new one down.
Yeah, so I'm just giving you a template. So for example, you can look at the hello world and, even this example, see what I'm doing, and try to repeat the value. Actually, the only thing that you may need to borrow from this code is this print statement, which you'll cover in a bit. We'll cover more detail in a bit. But over here we say print space star. So you can say something like this. So assuming temp underscore F is what is the result of converting Celsius to Fahrenheit, you can print it using the statement. Of course, you'll come to this more later. That's a little involved.
What's the formula again?
Yeah.
Check.
Yeah.
Still confused about how to run the. You said that you have to compile it first.
You compile it at the very end. So yeah.
So for instance, this an example of the hello world. So the way you compile, you just type the
Yeah, that's it.
So that's compiling.
Yeah. Right. And that's going to produce a file called a.out. Of course, you can change the names and all those things, but the reason it compiled successfully and produced that file is because we already had a working program. So now you're going to have to write this whole thing in a program, right? The proper working code, and then compile it. Of course, nobody gets the program to work the first try, right? You will compile it, it'll throw some errors, and then we look into the errors and like what's going wrong, So, and then go back, edit it, recompile it, so on, right? Yeah. So that's
so what's the difference between that and then when you type in the Fortran dash? Oh, that's for
yeah. So instead of saving your file called ./a.out, it's ./test. So when you execute it, you're not going to say the ./a.out. You're going to say .test, ./test. Thank you. And of course, just to clarify, the T bracket F, it just means temperature in Fahrenheit. And T bracket C, temperature in Celsius. So it's not two different characters, right? I think we should actually take a little bit of a break now, I think. So let's do a break. And let's come back at 11:40. Okay. Okay. It's 11:40. So a lot of ways to go. So let's get started. So for the temperature conversion, you can actually open up simple.f90 under the examples directory. And so basically, we've defined two real variables, temp C, temp F. And so what we're doing is basically doing 9/5 times 10. And of course, like this 10, you could have either used a variable, but over here, we're just saying 10, like a literal. So over here, 10 Celsius is converted to Fahrenheit. And similarly over here, 40 Fahrenheit is converted to Celsius, and we're printing them, okay? And so we're gonna run this program now. Simple.f90. So it's ./temp. So what you will see is 10 Celsius is converted to 42 Fahrenheit, 40 Fahrenheit.
Wait a minute. My computer says 1050 and 40 Fahrenheit 4.
Yeah, so 40 Fahrenheit is computed as 0 Celsius, which, it's like, isn't 32 Fahrenheit supposed to be 0 Celsius? So what's...
I use all real numbers. I didn't use anything.
Yeah, so the reason why that's incorrect is because over here, we're dividing 9/5, and these are integers. And what happens is in an integer division, 9/5 is just 1, okay? And so 9/5 is 1 times 10 plus 32, so that's 42. Over here, it becomes basically 0. 5/9 is 0 in an integer sense. So the correct way to do it is actually in the solutions. So if you go to solutions, temp.f90, this is the correct way of doing it. So instead of saying just 9/5, we put a dot at the end. You could have also said 9.0, but we don't need to. We just need to say 9.5. And the 10 doesn't matter because you're just multiplying with it. But just for the divisions, you have to say 5./9 or 9./5. Why? Because the output needs to be, when you're multiplying of a real number with a floating point number, a real number with an integer, the result is a real. But when you divide two integers, the result is not real. So this is the correct way to do it. So if you compile this program and you run it, you'll get the correct answer. So sort of a trick question, Okay, so let us proceed with the rest of the content. Okay, control structures. So far, we just talked about a linear execution of programs. So we just defined a variable, computed certain quantities, and then printed those variables. That's all we did. But real world programs are not so simple, right? You usually have to do many sorts of branching. So depending on some certain conditions, your code can take all these sorts of different pathways. So to do that, we have the control structures, the control constructs. So it's three different, or like several different types of them, 4 different types. So the first one is an if-else statement. So what an if statement and an if-else statement usually means, if a logical if a logical expression is satisfied, then you execute the statement. And even that can have 2 different or several different forms. In the first form we see on top, it's just if a certain condition is satisfied, then you execute the following statement. But in the second form, you see, you can check 2 expressions. So you can say, if expression 1 is satisfied, then execute all the statements in over here. Else, if expression 2 is satisfied, then you can execute these set of statements. Else, the else is just a default value. So if the condition 1, the condition 2, they're not satisfied, then it's the else clause that is executed. Of course, the else if is optional. Even the else is optional. So so all these are like equivalent form. Like you can use any one of them.
You don't need else?
So you technically don't need else, yeah, because you can also have like the first form. So for example, so if you have if value equal to 0, it's just an example. So you can just have if, and that's enough. So if
you want if and else if, I still don't need else.
You don't. Else just provides a default alternative. So you can just, if I go back to the previous, so the question is, if we have if clause and else if clause, don't we also need the else clause? And the answer is not necessarily. So you can just have if and else if, but you don't need you don't need an else technically. It's optional, because in that case you'd just be checking 2 conditions. So but else is nice to have because you always want a default, fallback, right? So of course, the important thing to note is that everything inside this expression, inside the braces, must be an output of a logical kind. So over here, when we do value less than 0, the result, it's a conditional statement. So it's going to have either a true or false value. It's not going to be, it's not a if, you can't, for example, say if value equal to 0. Not with a single equal to. You can use double equal to, which again is is a conditional expression. So it's checking if value is equal to 0, but you cannot use an assignment expression. So it needs to be a true or false value. So a little example. So for example, let's say the value of x, the variable x represents a student's score on an exam. And so you just have this a nice chain of if, else if, else if, else if. So this thing is, again, you can have multiple else ifs. You can only have one if statement for this corresponding block, but you can chain multiple else ifs. And finally, you can only have a single else for a single block. And after everything is done, you end if. So basically what it's doing is you filter, first of all, the lowest, less than 50, it's an F. Between 50 and 60, it's a D. So you see in this expression, you're combining 2 logical expressions. So it's like you want to check, first of all, that the score X is greater than or equal to 50. But you also want it to fall less than 60. So that's when this AND operator becomes useful, right? So these 2 conditions, X greater than or equal to 50 and X less than or equal to 60, they're going to produce a true or false. And so you can chain them together with an and or an or. But in this case, you need an and because it provides appropriate logic, because it needs to be both. It needs to be between 50 and 60, not either or, So, so then, the execution statement is what the grade is that is assigned. Okay. And I actually have another exercise for you at this point. So you know that the roots of the quadratic equation are ax squared plus bx, the quadratic equation ax squared plus bx plus c are given by q1 and q2, the familiar form. So please try to write a Fortran program. You can just assume the values of the coefficients a, b, and c, compute the roots, but now try to use an if clause to check that the discriminant, so the value inside the square root must be positive, right? Otherwise the roots are complex. So you're going to check if it's positive before doing the computation. So before these calculations are done, use an if clause to check that. And also you have to use an if else. So the else statement is going to just print that the roots are complex and not do the computation. So this is your exercise. Please try this, and the solutions are given to you. I'll have that page up. And I know it's not realistic to start coding up and also finish these examples, within the time frame of this course, but at least you'll start thinking about it and let me know if you have questions, but the solutions are provided to you. So you can always feel free to work on it after the class is over. Okay, so I'm going to show you the solution briefly, but we can also walk through it later. Okay, so we define the program, implicit none. We have a few variables, A, B, C, for the coefficients, D for the discriminant, Q1 and Q2 for the roots. So over here, I'm reading in the value of A, B, C, but you don't need to. So the important thing is first we compute the value of the discriminant, B squared minus 4AC. So we first check, is it positive? If it's greater than 0.0, then you do this. And yeah, so one thing I forgot to mention is that we're using an intrinsic function here. It's square root. So you just need to say sqrt bracket d. And then, so this, if this discriminant greater than 0, then you print out the roots. Else you just say roots are complex and end the program, right? So that's as simple as that. So fairly basic. And you can continue working on this. And if you have any questions, you can ask me now, or else you'll continue with the material. Okay, so the if, else if, and else statements, they're just one sort of like branching statements, depending on the condition. There's also this switch case statement, which pretty much exists in every programming language, same as if and loops. So what is a select case? We will look at an example. So for example, in this case, traffic light is a string. And we just say select case traffic light. If traffic light matches red, then we execute this line. If it matches yellow, then we print caution. If it matches green, print go. Case default is like the else equivalent. Otherwise, it's like just print, what the default values. So it's very similar to how the if, else if, statements work. The only thing is that it offers a little more like little less code, little less typing. It's much more nicer for these many sorts of multi-way branching statements. That is, depending on the value of a single variable, you have to do maybe 4 or even like 100 different tasks or something. So it's easier to write a switch case statement than it is to write, so many if else if statements. Similarly, you can also do, so what we did for the previous example, the same thing with a switch case statement. We select case score. So the select case and all these things are just Fortran keywords. Score is a variable, same as before. So between 50 and 59, we assign the grade D. 60, 69, it's C. So it's pretty much the same as this if else statement, only a little simpler, as you see. You don't have these complex logics going on, right? It's definitely like shorter code. So it's like cleaner to look at, and so on. So, and also like case default is like the else equivalent. And over here you assign the grade. Okay. So that, I think that should be pretty straightforward. So if, else if, else statements and switch case statements, these are all branching statements. But we want to do more than just branching. We sometimes want to repeat a same piece of code many, many times. So that's why you have like looping statements. So you have the so-called do loop, where I will show you an example. Okay. Okay, so we have a do loop. So this do keyword, what it does is it executes the statements between the do and the end do until this loop control thing is for as long as it's satisfied. And we'll come to some examples. So if you're already familiar with like loops in like other programming languages, then this should be straightforward. It's like for loop in many of the other, programming languages like C and like even in Python and so on. But the additional thing you can do with Fortran is you can also like give this a label. So the thing that you're seeing here within the square brackets, that's a label to this loop. So the do loop name is optional. And within the execution statements, you have two things you can do. Inside, if you say exit, it's going to just quit the loop at any point in time. And if you say cycle, somewhere in the middle of the loop, it's going to come back to the start of the loop and go to the next iteration. So we have a simple example of a factorial here. So basically, what is a factor? Like in a factorial, you just start, let's say the factorial of 6 as we're computing over here. We just start multiplying 6 with 5 times 4 times 3 times 2 times 1. The nice thing about putting a loop for this is that we can generalize the factorial computation. So if you write a computation for the factorial of 6, that should also work for the factorial of, I don't know, 1,000,000, So a nice way to generalize that is using a loop. So in this loop, we just have defined n with a value of 6 because we just want to compute the factorial of 6. So over here, we're initializing the factorial with a value 6. But the next time we want to multiply it by 5, right? So that's why you have a for or a do loop here, where you have this variable I. Notice that we already defined I here as an integer. And this loop counter variables, they have to be integers. They cannot be real because they count how many times this looping process or this iteration process happens, right? So it has to be an integer. It cannot be a real number. It cannot be a character, any other type. And over here, we say do I. And what this first number means is that it is assigned the value in the first thing. So it's assigned a value of n minus 1. So when I first starts, it's going to have a value of 5. Okay. And this next number here is saying that it should loop until I has a value of 1. And this third number here is the stride. So it's saying what should happen to the value of I in the next iteration. So let's walk through it. So initially I is 5, and then it comes to this statement, factorial equal to factorial times I. Remember, factorial was 6. So factorial is 6 times 5 now because I was 5. In the second iteration, it is decreased by 1 because that's what the third argument meant. So now I is 4. So in the next line, factorial is factorial times 4. So you already multiplied 6 times 5 times 4 this time. And then it, keeps looping until we go backwards in the index. And then finally, we print the value of the factorial, okay? So we also have the do while clause, which I'll give you an example for. So for the do loops, we had this sort of a counter variable, and we just can either count forward or backwards and so on. But in the do while, we have a logical condition. So we basically loop not until a certain number of time, but we loop until a certain condition is satisfied. So here the condition is I less than or equal to 100. So, and inside we are constantly updating the value of I. So for example, if let's say I was initially 1 before the loop started, and you never updated the value of I, you never incremented the value of I, it's always going to stay 1. And so this is going to be an infinite loop. It's going to run forever. So the only, so, you know, like this do while statement could run for as long as you want. So it's controlled by the sort of things that happen inside the loop, right? And an example that we show here is you can also have an if statement or a switch statement, whatever you want, nested inside a do or do while. You can also have loops nested inside if statements. So that's the choice is up to you. And what is this thing over here? Finite colon. That's just the label for it. When you read these long codes, sometimes you have like so many of these nested statements that you forget where you started the loop and where you ended them, or where you started the if condition and where you ended them. So these sort of labels make it easier for you to like keep track of them. And also you can also use go-to statements to jump to these labels, but that's we're not going to go into that because it's not recommended practice. So you have another exercise now. So we know that the summation of the first n positive integers is given by the arithmetic sequence formula. So basically, I want you to write a program that sums integers from 1, 2, 3 up to n and print out the result. So of course, just like the factorial, you want to make it general, right? So you're going to use a loop to do the summation. So in the factorial, we multiplied the factorial within by itself, you know. But over here, we're going to sum. We're going to keep a cumulative sum, okay? And so this whole thing, that's the left-hand side. But of course, the right-hand side, n times n plus 1 over 2, that's like the theoretical formula, right? Of course, here, you know it's going to match it because it's a simple math. So you're going to have an if statement. So after you have the do loop, and the do loop finishes and you have the sum, you're going to have an if statement to check if the code matches this thing on the right-hand side. Okay, so that's your exercise.
That may be it may not be integer, it may be something else.
Okay, that's a good question. So the good thing about this is everything here is integer, and
oh yeah, because n and n plus one of the numbers has to be.
Exactly. So yes. So thankfully, it'll still be an integer.
Okay, thank you. How many integers do you want? Oh, got to read it.
So I would suggest, of course, you're going to need an integer to keep track of the loop, right? And you're going to have an integer to keep track of the sum. And you're going to have an integer just for the value of n. So I'll leave the factorial thing as an example for how you may want to do it. But remember, the factorial is counting backwards, but you want to count forward. And over here, it says integer kind equal to 8. I would say you can ignore it for now. So you don't have to say kind equal to 8. That would be required if you're computing the factorial of very large numbers, but or like the sum of very large numbers, which we're not going to do right now. So you can skip that. Okay, so in the interest of time, we have to get going, but the solutions are given in this file under examples solutions. So it's summation.f90. You can take a look at that later to see how that's written. Okay. So now we're going to talk about some other interesting things. Of course, it's like we have like maybe like 2 hours to discuss a Fortran programming language, which is obviously not enough time, but so it's like this course hopes to sort of give you some basics and give you a flavor for what else is there. So like we talked about a program, a main program, and so far we've talked about declaring variables, like linearly executing statements. We have talked about branching operations. We talked about loops, and so on. But we can do a lot with just that, with just this main program and all that. But a Fortran program can consist of one or more like program subunits. They're called like subroutines or functions or modules. Why do you want to do that? Because like anything that's not a very simple piece of code is going to inherently turn like very complicated. If you like, if you want to do any like any sort of moderate to intermediate like computation, your code is going to get lengthy. Lengthy codes are harder to read, harder to maintain, and there's so many reasons why you want to like split up your big chunk of program into like smaller blocks. One of my favorite reasons is the so-called unit testing. And so what that means is, let's say you have like a really complex piece of code, but one part of the code just does some basic, like a very basic piece of like operations. But the code, let's say, is like 10,000 lines long. If I'm writing a 10,000 line code and I want to test this small part of that code, which is just 100 lines, I don't have to like finish the whole 10,000 line program to check the 100 line piece of code. And so it is nicer to branch it off into a subunit, a program subunit, so that I can do unit testing. So I can write these small chunks of programs, which does like very smaller tasks, and then I can test them separately, right? That's called like modular programming. So that's very useful. That's almost like crucial if you're writing like a big program to like split your tasks into smaller chunks. And as a plus, like you also like avoid rewriting code a lot. A basic example, I think maybe I'll skip this, but so what is actually, let me go to this example directly, okay? So there are two types of at least three types of program subunits, but we're looking at subroutines and functions. So a subroutine, so for example, the subroutine is going to add, like we're writing a program to add to real numbers and return the result. Now we could have done all this code in just a main program with just program, calc and end program. But to make things more modular, we've moved that operation into a subroutine. So we defined this with a subroutine keyword and ended with a subroutine keyword. And again, like whatever happened in your main program, like implicit none, you still have it same way. You still define variables the same way. But what is new is that your main program didn't have all these arguments. So what are these doing here? So so basically the subroutine gets some input from the main program. So below, I have an example of what the main program does. In the main program, all we have to do is say call and then the name of the subroutine with the arguments. So in the main program, let's say the variables in the main program are actually X, Y, okay? And you wanted the value stored in Z. So this X translates to A inside the subroutine. This Y translates to B inside the subroutine, and C translates it to Z. So what happens here is that over here, what you're doing is we're just adding C equal to A plus B. But when I call the subroutine from the main program using this thing, in our main program, Z has the value X and Y, because all that magic operations are happening inside the subroutine. And so from the main program, you don't see what is happening inside. You just see, oh, you know that it's going to do the summation thing and it's going to return the value in Z. So that's all you're concerned about. And similarly, you have subroutines, you also have functions. In the function sense, it's very similar to a subroutine. The only big difference is that you see how it's being called. In subroutines, we call calc XYZ. In a function call, we don't use the call keyword. We just say the name of the function and we pass in X and Y, and the result we get in Z. Now in function, the interesting thing is we don't have a C anymore. Instead, it's the name of the function that is what will be returned. So in this case, whatever you've passed to the subroutine gets changed. But over here, the function returns the value, like it computes A plus B, and then it returns the value to Z, if that makes sense. So of course, there's like a lot more to explain here, but in the interest of time, we can't get into it. But yeah, so basically these are functions and subroutines. And I think later you'll have an example of, so for example, this, let me go down actually. Okay, yeah, so the same quadratic root equation. So after the class, if you want to get your hands on, experience at writing subroutines, you can convert your previous program. So first work in your previous quadratic roots program, make sure everything is good, and then try to use the subroutine version of it. Like instead of doing all the calculations in the main program, transfer them to a subroutine. And you also have the solutions to that program over here. It's called quad_subroutine. Okay, so you can take a look at that later. Okay, so I'm going to skip recursive functions because it's probably not as essential Okay, so I said there are many ways of writing subprograms. A module is one such thing. So like the subroutines and the main program actually go into the same file. Maybe let me show you what I mean. Okay, so over here we have the main program, right? And the end program. And in the same file, we also have the subroutine. And this is the solutions to your exercise. And in the main program, I say call quad roots, with all the arguments and stuff. But what if I wanted to move this subroutine and all its contents to a new file? There are many ways to do this, but one of the ways is to define a so-called module where now we can move that entire, so it's like a self-contained unit that can have data and functions or subroutines. So it's like, of course, it's like, you can have like an entire 2-hour talk on just how to do like modular programming. So it's like a big topic, but on a basic, very surface level introduction, it lets you write self-contained blocks of program to do like very small chunks of data and operations. So, and you can use, if you see a use statement in a Fortran code, that's what it does. So the use keyword followed by the name of the module means now we can make use of whatever data and functions are there in this module. So in this case, I have a program test and I'm making use of this module. And suddenly I can call this function calc. So I can, after this use statement, and note that it comes, it comes right after the program definition, right? So because of this use statement, I'm able to call the function calc that resides within this module in a separate file. So there is a special procedure for how to compile modules and how to link them. It's no longer just simple G Fortran, test.f90. It's slightly more involved. There are a lot of other things to discuss, but this is probably the most important thing, which I haven't gone through a lot. So simple input and output in Fortran. So this is the first example we tried. So what this program does is basically we define a string of length 100 called your name. And when we want to print a string to the command line, we use print star the string. And it can also be, let me show you. It can also be, you can either use print statements like this. You can also use write. So in this case, what I'm doing is I have write, comma star. We'll get to why there are stars here. And over here is the string. So this is a string literal. So it'll print as it is. Anything that is within the double quotes will print as it is. But then we have to print what the value of the root is, Q1. So to concatenate it, we use commas. So within single quotes, the roots are comma, Q1, comma, and again, this will print as it is. It's a string literal. And then it's a comma, and there's the second value. So now, in this example, Fortran is automatically deciding. So we know, so Q1 and Q2 are real variables. So meaning they have a certain amount of precision, right? So many digits after the decimal places. So Fortran will choose a default way of representing it and printing it to screen, okay? And that is kind of why we have the stars here. And I'll come to that in a bit. So we have the right, we saw the print statement, we have the write statement. We can also read a value from the command line using the read statement, read star, comma your name. You can also use the read statement like this. So you can say read star, comma star, A, comma B, comma C. So in this case, it's expecting three variables, okay? So in this case, we expect 3 variables, and when you press enter, the values are stored in A, B, and C. So that's what happens. So instead of, so we saw this read and write, and the first character within the braces was a star. And what that star actually refers to is a so-called unit number. And so when you use star, we're actually saying it is the same as 5. Or when you say write, we're actually saying 6. So that's the standard unit number. And because we don't want to remember 5 and 6, we just say star. And why is this 5 and 6? It's 5 and 6 because we're reading and writing from the command line. But we could also be reading and writing from files, either text files or binary files. So that's where things get a little more interesting. Now, obviously, that's a little more intermediate course, which we can't cover, but there are some examples and, of course, materials on the internet. And so that is what the first of these star means. The second of these star, and I'm going to skip to the these parts, the file operations. The second part, I'll give you some examples. So instead of saying star, you see how these are real numbers, right? So instead of saying star, so we could have said something like this. So what this does is it formats your variables array2 in a certain way. First, let's go to a simple example. So let's say in the first line, you want to print I, okay? So over here, I we expect is an integer. But if you want to tell Fortran to print I with the width of 5, that is, you want to print 5 digits. And even if I only has a value 2, you don't just want to print 2, but you want to print it with the width of 5. So, it's like padded appropriately. So that is what this I5 means. Okay. And here, things are a little complex now. So A, B, C, Z are like real numbers. And even Z is a complex type, but it's still real. But because now we have like 3 real numbers and 1 complex, that means you have 5 real numbers in total. Because remember, like complex was, it's just a pair of real numbers. So this 5 at the start just refers to apply this formatting to all these numbers. So apply this integer formatting to this I, and then this F refers to floating point formatting for all these other numbers. And so 5 just refers to the number of floats, and this 12 is the total number of numbers that are represented. And the .6 just means how many digits in the after the decimal place do we need. So that is represented by the .6. Okay. So these, of course, you need to try it out for yourself. So I'd recommend, so there are like resources linked from the short course page where it'll take you to more ways of like describing these format statements, right? And this page describes what the exact formatting is. I'm going to quickly check if there are any questions. I mean, I included array handling as a intermediate topic if we had time, but it looks like we're out of time. But very briefly, I want to say that Fortran is very good with like array multiplication and some things. So like, so just some basic examples of how to declare arrays and how Fortran, so Fortran uses the column major order of like ordering elements in an array and storing them in memory. So that's important to know if you're using arrays. And so just some examples for you to look at, some basic matrix multiplication. So yeah, I think we're out of time. So with that, I'm going to stop. Reminder that you have a lot of examples to play around with. So all these example files, you can compile and take a look at them. And some of the solutions to what we talked about, they're also here. So I think, probably sufficient enough resources if you're like very new to Fortran, and we can check out the online resources that we have. From the short course page, takes you to like just tons of resources. So you can follow up with that. So
where's your slide?
for the slides, they're on the home page, the short course page, and you just click on the PDF, the first line. This one. Oh yeah, so let me quickly show you how to do that. So if you go to hprc.tamu.edu, you go to events, short courses, and then you'll see a list of items, but if you scroll down, you'll see Fortran, introduction to Fortran. Click on view details, and then you'll be taken to this page. Yeah. Cool. So if there are no other questions from the Zoom folks, thank you for listening, and hope you found some things useful.
Thank you.